So welcome everybody. Our next session is mainly about vector spaces, which is the main topic, and also vector multiplication, which are the main topics of our exercise sheet 3.2. But I want to, to return just for a moment to the optional exercise from last sheet, which is about application to electrical circuit in the case of a system of linear equations. So you were asked to, sorry, I have to shut you down for a moment because I have some disturbance. So it's about Kirchhoff's laws, additionally to the well-known Ohm's law, which is the basis of everything in electrical circuits. Of course, let's start out with this. It's sometimes also called the Uri law because it's easy to remember if you write U equals R times I. By the way, I know that in the English-speaking regions, it is more common to say V instead of U for the electrical voltage. I should perhaps use this, but I stay with the let's say with the German notation. So because the disadvantage of this notation is that the symbol for voltage is in this case exactly the same as for the unit of the voltage, which is called volt. You know, it's of course the same word. Goes back to Volta, the person who to whose honor it was called this way. So anyway, in this case, you can't really distinguish between the physical entity and its physical unit. In this notation, it's clear. With U, I mean the voltage as such, and with V, I denote its unit, okay, which is volt. Anyway, we don't have, yes, we have numbers. Here you see it, okay? So in this case, the outer or the only energy source in this circuit is one with a given voltage U0, which has a value of 300 volts. So now you see the difference. Anyway, that's Ohm's law. It says that voltage equals resistance times electrical current. That's the important thing. And this is what we use all the time. But additionally, we have Kirchhoff's two rules, which are the following. The first one is called, or one of them is called Kirchhoff's mesh rule. Sometimes it has also some different names, but I call it Kirchhoff's mesh rule. A mesh, of course, in a current is like, it's a closed, yes, how do you say, something like a cycle or a circle, whatever, but it doesn't, this is not, I don't mean this word by word. What you see here is that theoretically an electron could take a closed path. Yes, let's just call it a closed path in this circuit. And here's another closed path. And also we could go all around, even this is a mesh, but these are the so-called elementary meshes. And it turns out that to set up a complete system of linear equations to solve this exercise, which means to calculate all the different currents in this circuit, you have to set up exactly one equation for each mesh, for each elementary mesh. Sometimes there are some problems with elementary meshes, and then it's also allowed to use, for example, this one like a combined mesh, but then instead of one of the elementary meshes. So here, there's no reason to do anything special. We just decide to use the elementary meshes, which I numbered with 1, 2, and then in this case, I go counterclockwise. No, I go clockwise. I could do it this way or the other. This doesn't matter. But if I go clockwise, I have to regard these current arrows because they decide whether a contribution to the whole equation counts positively or negatively. That's the mesh rule. The mesh rule principally says that the sum of all voltages around one mesh equals 0. And here, this is, in the end, it's nothing else than a certain form of energy conservation. You must know that electrical voltage is nothing else than electrical energy per Coulomb. So electrical energy in joules divided by the unit Coulomb, which is the SI unit of electrical. I don't get the word now, Lado. Sorry, I just don't get it. Can you help me? The amount of electricity in the SI unit Coulomb, which is a quantity of, okay, now I have it, quantity of charge, it's called. I'm sorry, I just forgot the word for now. Okay, so the energy in joules divided by the electrical charge, something like joule per Coulomb. So this is a sort of energy. And if you go around one time and you arrive where you started, so the whole energy you consumed equals 0. But this affords or requires that you consider the sign, which means you must consider the direction in which the current is flowing. In this case, if I go around one time, once, then you see how the first equation comes along. It's, I go along current I1 over resistance R1, and due to Ohm's law, the corresponding we call it a consumer voltage of this consumer here, because every resistance in the circuit is a electrical consumer of electrical energy, and so the voltage here along here is the resistance R1 multiplied by the current I1. So that's a contribution to this sum of voltages, the first one, right? The second one is around here is I2, R2 times I2. And then if I go on, as you see, I go in opposite direction to this source voltage arrow, which now means that the energy or the voltage that is consumed by these two elements is compensated by the energy, you could say, supplied by this source, okay? So that's why I would have to write minus U0 and then equals 0. But then it's usual to put all the source voltages to the right side of the equation. So that's done. And the same thing happens with the second mesh here. Now, I think now you know what I'm doing. Also, you have to recognize that this node K2 is not a real node. It's not a real node because the current I3 just flows here and then it goes on over R4. It means that these currents I3 and I4 from the original exercise are actually the same. So it's not even necessary to regard this node. And I just crossed it out and said, okay, we call this same current E3, I3, 4, or even just I3. So we have three unknowns, which are I1, I2, and I3 in the whole system of linear equations. So that mesh takes on, look at it, I go around here. Firstly, I go, you see it's the same, this is a connection branch of the two meshes, which is now this time reached upwards or transverse upwards against this I2 current arrow. By the way, it might turn out that one of these current arrows has been drawn in the wrong direction. This is not a problem, because then if you solve your system of equations, you will find that the respective current turns out to be negative. If it turns out negative, you can correct the current arrow after your calculation, and then everything is fine again, and then you will change the sign with your result. So that's the usual procedure. Anyway, with this arrow we have minus R2 times I2, then we have plus, I call it I3, flowing over R3, so we have a plus R3 times I3, and then also plus I3 going on over R4, so R4 times I3 again. I can, yes, I can bracket, put these in parentheses, R3 plus R4 times I3. And as you see, that's it, because we have no energy source inside this mesh. In the end, that's another correct equation. And so the next thing is Kirchhoff's node rule, which says that the sum of all currents, here you see it, which flow into or out of one node is also equal to 0. So why is this? The reason is also these currents, it's quite the same as with the voltages, have to be taken into account with correct sign. And the convention here is what flows in counts positive and what flows out counts negative. If you look at this node K1, you will recognize that I1 flows into it, while I2 goes out of it, and I3 also goes out of it. So that means this is a so-called current separator. It's like I1 is separated into a part of it, it is I2, and the other part is I3. So it's obvious to see, I just crossed this out because I replaced them all by, perhaps I could do it a little easy, like this, okay? So I just call it I3. Of course, it's not disappeared. It just has been identified also with I4. That's what I meant, okay? So in the end, it's obvious that the sum of I2 and I3 must be I1 because this flows in and these two flow out. So that's what we do. This counts positive, these count negative, and that's why I write I1 minus I2 minus I3 in sum equals 0. It's nothing else, okay? So now you see what we get. We get a regular linear system of equations with first, second, and third unknown, and on the right-hand side, you see it's inhomogeneous. It's inhomogeneous, quite surely, because we have at least one energy source, and that's it. So all the rest is filling in the numbers. And what I did is, because they are all multiples of 100, I took this factor of 100, just drew it outside, you see, so that it's a little more comfortable, because the whole thing is, and I would have to write here, look at this. What we have is that the first resistance is 100 ohms. The others are all equal to 200 ohms. And the voltage here, the source voltage, is 300 volts. It means if I put this in 100, and I just leave away the physical units for calculation then, yeah. So I have 100 times I1 plus 200 times I2, and then equals 300. And here you see that I just said it's easier to write 1, 2, 0, and then equals 3, because I could easily take this this row by 100, and then it would be the actual values. It's just in parentheses as an annotation to tell you that the lower numbers are easier, and this is why I use them. It's always allowed to scale an equation with an arbitrary factor. Okay, so I can also draw it out. The same I did in the second, and in the third one it's just as it is, and then the rest is just regular Gauss or better Gauss-Jordan elimination, of course, and that's what I've done here. And in the end, I get my diagonal form for the matrix, which has numbers of 7 everywhere on the diagonal. Here positive, here negative, and so I divide the lines by their diagonal elements. And then I have my unit matrix, and I can read the solution on the right side, which is then after all, I fill in the correct physical units again. So my currents are 9/7 amperes for the first one. The second one is 6/7 amperes. And the third and fourth one, as you know, they are the same, is 3/7 amperes. And this corresponds to the official solution from some other source where this exercise was taken from. So that's what I wanted to tell you in short. And if you have any questions, you may ask them now.